So follow-up to the previous presentation, let's discuss a bit software-defined radio implementation of two-way satellite frequency transfer receiver and transmitter. So here the novelty is that we're doing a completely independent system by developing the transmitting system. So this is work in collaboration with between Besançon Observatory, LNE LTFB, and Paris Observatory, whose two-way VSAT satellite system we're using. So if all you care about is the result, that's a result of 3 weeks of two-way time transfer between Paris and Besançon using, in pink here, the SATRA modem, so that's the operational system during the UTC even hours, and in green, the SDR system that we've been developing. And in terms of island deviation, that's the SATRA result. In orange is the SDR result for 3 minutes durations. And we're broadcasting because we're working during the test odd hours. We're free to run this for 5 minutes. So of course, if you average more, you have better results. So that's the SDR result over 5 minutes. So let's think about the results. Now, destination is not the objective here, it's the path that's interesting. So that what I'm going to present to you is a bit the challenge that we met and the results that we learned when reaching this result. So I'll quickly introduce what the challenge is in implementing the transmitter and receiver. On the emitter side, how we developed the fully FPGA standalone emitter hardware, drift on the X310 receiver that we're developing, how we're working on the post-processing of reception, and a simulator, because it's kind of annoying to be always asking the guys on the other end of the link if they can run their station, so we would like to have some sort of simulating system. So first of all, what are the challenges? I'm not sure if it's obvious to everyone, but what I find a bit annoying here is Telstar, in the two-way satellite time frequency consortium, they're renting 5 megahertz bandwidth. And 5 megahertz, like the inverse, is 200 nanoseconds. So if you sample a 200 nanosecond period, you have the full information. And the objective I was given at the beginning of this project was you need to measure the time with 10 picoseconds. You need to find a 1,000-fold improvement on the between your sampling period and the time delay. So that means that you're going to show a lot of artifacts, a lot of things related to signal processing that you would not usually have in your classical Shannon condition. So that's a challenge that we needed to meet and that we discussed already last year in Toyama. So I'm not going to go so much into the details, but basically you're sampling at 5 megasamples per second, 200 nanosecond period. You overfit by polynomial fit, second order polynomial fit, parabola fit of the cross-correlation peak. You create a lot of artifacts if you just do this within just Shannon conditions. So you have to oversample a little bit, zero padding, which is your sync convolution of the data, and that will allow you to have 1,000-fold. Actually, you can demonstrate that the improvement on the timing resolution is equal to the signal-to-noise ratio. And as opposed to GNSS, geostationary satellite link is a high signal-to-noise ratio condition, so you can actually reach very strong improvement on the correlation peak position. So on the transmitter side, what I wanted to do is something as simple as possible. As I discussed yesterday, the fewer analog components, the better we live, because the fewer drift, the fewer things to characterize. So basically, the transmitter is just an FPGA. The 70 megahertz carrier is generated, the BPSK modulation, and the total random sequence are all generated in the FPGA. Originally, we wanted to have a compact embedded system using the same FPGA as a receiver. SDR, this is still an option, but if you're developing an FPGA, you know that synthesizing the X310 gateway is something like a 3-hour synthesis, and when you're developing, it's super annoying. So we went back to the drawing board and took just a very basic FPGA for development. Here, the synthesis time is a couple of minutes, and once we finish everything, we're going to integrate in the B210 or X310 as FPGA, but at the moment, it's a separate system. Now, the other thing that we realized at some point is, okay, you start broadcasting, so you've got the 10 megahertz, which is clocking your FPGA with a lot of pills of signal shaping. You've got 1 PPS that triggers the generation of a total random sequence. Everything, so carrier, BPSK, are all generating FPGA, and actually there's a payload on top of this we're not going to care about. And whenever you're doing SDR transmission, you know that you've got a lot of unwanted parasitic spectral components. So surface acoustic wave, bandpass filter, and loopback path to measure the time of the reference time and the one going to the up converter and down converter. Here we're using the VSAT system provided by TimeTech when they installed the two-way satellite time frequency system. So you see here, this is the black is the SAT modem transmitter, the blue one is the FPGA output, so our SO device obviously is rejecting there the sidebands here, but basically within the bandpass we are matching a power condition. Now the satellite, as we just seen a few minutes ago, is moving in space, and typically the motion of your satellite is going to be a few nanoseconds per second. And what happens here is that if you miss the 1 PPS trigger signal here on both ends of the communication, well, your two-way time transfer double difference is not going to subtract the satellite position, because the satellite will move away by 5 nanoseconds or a couple of meters between the two subtraction times. So the condition is if the satellite is moving at 5 nanoseconds per second and you want to measure time differences with sub 200 picoseconds, which is the objective I was given, it means that your two outputs must, or your two transmitters must start broadcasting within the same 40 milliseconds. Otherwise, you will not cancel efficiently the satellite motion. Which is a bit of a chicken and egg problem here, because of course here we're working with already synchronized stations. So it's easy because you just say, I trigger my FPGA on the 1 PPS start a rising edge, and they both start broadcasting at the same few nanoseconds time difference. But when you're in a completely random state at the beginning, well, you will start with a very poor condition where you cannot cancel. The satellite acts as a converter from millisecond to nanosecond offset, and slowly you will converge. But at startup, it's not completely clear to me how this is going to converge. But at the moment, we're working with a functional system, so we don't really care about it. So that's the transmitter side, as simple as possible to be reproducible, and just to solve this problem here of making sure we're on the same PPS. Now we have an active monitoring of the NTP, and when the NTP switches to minute 59 seconds, then we enable, and the FPGA will start broadcasting on the next PPS. So now we solve the trigger problem, which had plagued our communication for a year now. The processing is, we're recording everything in the post-process. We don't want to do real-time processing. So that also means that we don't have limitation on computational power, we don't have limitation on the number of channels. We just record everything for 5 minutes. 5 minutes, 5 megasamples per second, 16-bit samples, complex, loop back, and downlink is 40 megabytes per second, 13 gigabytes in 5 minutes, or even if you want to make 1 hour sessions for 144 gigabytes, you can all buy for 90 euros 1 terabyte SSD, and that's going to fit. So that's now feasible to just store the 144 gigabytes in an hour and then process during the even hour when the real guys are communicating the practical sessions. And we would like a system that is hardware agnostic. And it amazes me that metrology people are all using the same black box. You don't know what's happening in the SAT. You're using, if you have a common mode error, you're all using the same stuff. So I would like this to be hardware agnostic, so that we're sure that if something is wrong, we see it and we don't hide it under the carpet. And what we're doing here is we have these two X310s. And in the beginning, I was just doing the two-way time transfer. We had sub 200 picoseconds. I was super happy. And I didn't understand why the individual standard deviations were worse than the two-way time transfer standard deviation. How come that when you do the subtraction, you get a better standard deviation than the individual guys? Until we looked at the loopback signal. And what we're doing in our system is the X310 sleeps, wakes up at the second before the broadcast, starts emitting the signal, and then we start recording, meaning the FPGA and the ADC are cool. And then for 5 minutes, they just keep on accumulating the data, warming up, and then they sleep again. But we have the same X310 in Paris and in Besançon with the same temperature control, the same setup. So actually the two X310s are drifting at the same rate. And you see that it's not negligible. I mean, over 5 minutes, you're drifting by 150 picoseconds. So of course, if you're using the same hardware on both ends, you don't care because this is going to be cancelled in two-way time transfer calculation. But if you want this to be running on one guy's B210, on another guy's X310, on another guy's proprietary SDR they want, well, these guys are not going to be cancelled out. So these are things that you need to identify if you want to have a reliable, understandable system. Now, the solution here, if you saw a bit earlier, I hid it. No, actually, I didn't hit it. I forget to put it. So at the moment, we're storing the file, and the solution to this is rather than storing the file and waking up the SDR just before the broadcast, you actually stream the data continuously. So you have a 0MQ or UDP output that tells the SDR to continuously broadcast information, and you just grab them when you need them. So this way, the FPGA, the A to D converter stay warm, and you avoid this risk. Which is exactly, so this is one thing. The other thing is tuning the power. So we saw that the uplink power was matching the SAT transmission and the TLSTAR requirements. But on the downlink, when I installed this, I was not in Besançon, I was in Paris, and I was looking at the X310 outputs. And usually in the Blue Radio, when the signal saturates, Blue Radio works with normalized value plus or minus 1. And I was increasing the gain, putting more and more amplifiers, and it never reaches 1, so I put more amplifier, and still not 1, so I put more amplifiers. And we ended up communicating with an excess of about 18 dB, because somehow, this I cannot explain, but the X310 with the basic RX, which is you're feeding directly the A to D converter, never reaches plus or minus 1, it starts compressing before, and as you increase the input power, the output signal saturates at about 0.55, 0.6, and I was just putting more and more amplification. So just be aware that the X310, if you want to use it at full scale range without saturating, you should limit the downlink power to 6 dBm. After this, you have nonlinear effect and awkward behavior. And this you see directly on the standard deviation. So each one of these time slots is a 5-minute acquisition. So when you wake up the system, you see here the drift by 150 picoseconds in blue line here where you're drifting. After 5 minutes, it starts stabilizing. After another 5 minutes, it stays the same level. So basically, after 5 minutes, you're stabilized. And then you put an attenuator here because you realize that you're putting so much power in the X310 that it's behaving non-linearly. And then you see your standard deviation and your line shrinking. So if you put this not at time domain graph, but as a standard deviation as a function of power, you see that in the condition that we're working in, we had far too much power. This is an attenuation here. So we had an excess of about 18 dB, sorry. Then we reduced by 12 dB, but that's not still good enough. We're still saturating. Then we put another 18 dB attenuator, and that's where you get the utmost performance, so sub 10 picosecond standard deviation here on your loopback signal. And if you're not careful enough and you just wake up the SDR and don't keep it warm, you see again you have this temperature drift. Even though you attenuated the signal good enough, you still have this poor standard deviation because it's drifting at wake up. So this is your actual curve of the standard deviation as a function of power, and this is just an outlier because we did on purpose wake up the SDR and then do the data collection. And then I mentioned that that we would like to have a simulator because always asking the guys in Paris, can you wake up your station and can we do a two-way time transfer? And you don't know what you're doing. So doing a Doppler shift simulation is super easy. You all know that you just frequency offset your clock and you created a Doppler shift. That's easy. But we want to introduce time shift of a few nanoseconds per second. And that's where going back to the good old analog signal. Historically, our lab was doing piezoelectricity and acoustic delay lines. And so I asked my colleague, William Dagneau, to design a 70 megahertz time surface acoustic wave delay line. It's kind of big, it's 21 millimeter long, because if you want to have enough temperature, because we're using temperature drift here, so lithium niobate has a high temperature sensitivity, and if you want to introduce a few tens of nanoseconds time offset continuously as you're moving the temperature, well, you need kind of a long time delay. So I let you do the calculation, but to get the 5 microseconds through the temperature sensitivity of lithium niobate, if you shift by 100 Kelvin, it will introduce 37 nanoseconds for the temperature sensitivity, and that means you have a 21 millimeter long delay line. But it's a relay wave, so you have very low losses. Your losses are only introduced by the electromechanical coupling coefficient of lithium niobate, not by the propagation loss. Relay wave has negligible propagation loss. If you take the time domain, you see here the 5.6 microsecond trip, and then you've got the triple transit, because this guy here is acting as a re-emitter, so you've got all the triple transit, so you've got 6, 18, 24, and so on microseconds. These are the ripples. Even though you're putting acoustic absorber here, you will still have a re-emission of the strongly coupled material. But you don't care because these are well beyond the correlation peaks that we're working on. And so you can, yeah, okay, that's not yet updated. So you can have a simulation where you're I can send you if you're interested. So you can do the simulation, warm up the lithium niobate, introduce a few nanosecond per second time offset, and it allows you to perform the simulation of not only the frequency offset, but also the time offset. So to conclude, basically we have now assembled a complete testbed, hardware and software, allowing to demonstrate two-way satellite time frequency transfer using only software-defined radio. The objective is that the user can understand all the details and can assess all the parameters. At the moment, it's just basic DPSK because that's all we know how to implement. Actually, QPSK is implemented, but we haven't used it yet, so we're still debugging DPSK. I would love to see someone help us with BOC or anything that, I mean, what the people of GNSS have been developing for the last 30 years is not being used in two-way time transfer. It's beautiful to see all this stuff being used now. If you're interested in contributing, please clone the GitHub repository. You'll find all the tools and let us know what we missed in the documentation for you to reproduce. To do, you need to stabilize. We made a 3-week demonstration. We're struggling to repeat the demonstration, so we need to do this for a longer session, demonstrate this for longer duration. At the moment, I'm doing super simple GNSS acquisition phase, so just correlating and peak fitting. We need to implement the full tracking DLL, PLL, that's a work in progress. Calibration, we just heard about calibration of the passive system. This device also needs to be calibrated, so at the moment, we do have the PPS output from the FPGA, which we need to calibrate with respect to the PPS input. This, in the plan, is to be completed by the end of the year. This is what we included in the project management. And at the moment, we're still using a commercial VSAT up converter, down converter. And it will be beautiful now with analog devices providing 11 gigahertz, 14 gigahertz PLL as off-the-shelf chips to get completely rid of the analog and do a fully digital system that will uplink at 14 gigahertz and downlink at 11 gigahertz. And with this conclusion, I thank you for your attention.